One of my favorite things about being on YouTube is that teenagers all over the world write me and ask me to do their homework for them. There is one particular problem that I like. This problem here, this is really good. It says, equal masses of melting ice and steam at 100 Celsius collide and mix. I want you to notice there are two key ingredients they've given to us. First of all, okay, fine, I'll say that equal mass is important. But notice this says melting ice. Now that means that the ice is at 0 Celsius. And they say the steam is at 100 Celsius, and so we got equal masses, and they're both about to change phase, so all we need to worry about is the fact that the changing of the phase will take some energy or release some energy, and the changing of the phase will take some energy or release some energy, and then we also have to consider the energy that goes into changing the temperature of the water that results once the ice has melted or once the steam has condensed. So I wanted to do this problem, but I got really distracted because I looked up some numbers. So let me show you, I'm going to walk you through. If you want to skip ahead to this time right here, you could just do that. But in the meantime, if you're interested in steam and ice, I kind of was. I looked up the density of steam, and I found that to be, well, at 1 atmosphere. The density of steam at 1 atmosphere apparently is 0.590 kilograms per cubic meter. And then I fiddled around a little bit and found the density of ice at 1 atmosphere, and that's actually quite a bit more. I hope you were presuming that it was quite a bit more. I found it to be 0.92 grams per milliliter, and that was really annoying, so then I had to get back into the same units. Now, I noticed that I could just multiply by 1 a couple times, because that doesn't change a number. What am I going to do? I'm going to take, where's my TI-80 blah blah blah? I don't know. I want to get grams into kilograms, so I got to kilograms down here and kilogram up here, 1,000. And then I probably want to get out of milliliters and get into cubic meters. I happen to know that a milliliter is a cubic centimeter. 1 milliliter equals 1 cubic centimeter, and that means that I've got 100 in this direction, 100 in that direction, and 100 in the depth direction, so I'm talking about 100 cubed of those. That's a million, so 1 million milliliters, 10 to the 6th milliliters, is 1 cubic meter. So if I do all that math, oh man, I don't need my TI-80 blah blah blah, this is just going to be 920 kilograms per cubic meter. And what I thought was interesting was the ratio of those densities. So the ratio of the density of ice over the density of steam, ew, this marker is rough. This is our operative ratio right here, 1,559. That means to me that we have, if these are both at atmospheric pressure, and let's assume that they are when this collision occurs, that means that we've got 1,559 times more volume of steam than we do of ice. I mean, I could do a quick calculation, but hopefully you'll believe me that the volume of steam is 1,559 times the volume of ice. Ooh, ice, yikes. Okay, so we're gonna take these guys and we're gonna do a little thought experiment. Let's assume that there's a tanker truck holding the ice. Can you imagine the largest tanker truck you've ever seen on the highway? And there's this driver up here in a big old truck, and it's shaped kind of like that, and there's a whole bunch of wheels back here, wheels all over the place. Wow, there'd be like wheels over here, wheel up there. What, 18 on? Wow, yeah. This one's so big it's got 18 on one side. Just kidding. All right. This guy right here, its volume, I looked up its volume. Apparently the volume of the largest tanker truck that you can imagine is 43,900 liters. That's the volume of that tanker truck. But that's pretty quickly converted into just 43.9 cubic meters. So you could put that much steam in there. And I was wondering, how big the ice would have to be then to have the same amount of mass. So I took this number and I divided by the ratio of the volumes, and I found a volume that's, wait for it, the volume of ice that you need is, oh shoot, did I write that down? Yeah, I did! The volume of ice that you need is 0.028 cubic meters. That's a much smaller number, in fact, by a factor of 1559. So then I took the cube root of the volume. What's that gonna give me? Oh, that's gonna give me the side of a cube. And I found that side of the cube to be equal to 0.3, almost exactly 0.3 meters. Curiously enough, in the United States, we have all these rulers that go to just about 0.3 meters. Oh, ew, yuck. Well, anyway, if you take 0.3 meters and make yourself a cube, then you'll have, guess what? You'll have an ice cube whose volume is 1 cubic foot. That's stupid. What's really important is you'll have the mass of ice that's equal to the mass of steam at atmospheric pressure that fills up an entire tanker truck. Wow. Okay, cool. So you're saying if I melted and boiled a cube of ice with that side, then it would fill up a tanker truck at atmospheric pressure. Awesome. Okay, so now we're gonna get back to the problem that kid asked me because he didn't want to do his own homework. And the problem is this: the equal masses collide. And so I wrote down a couple numbers. I wrote down the latent heat of vaporization. And that's latent sort of means hidden. And so that's the heat that's going to be released when the steam condenses. And it's got a value, and that says let's call it 2258 kilojoules per kilogram. And a lot of times this will just be presented as 2.258 times 10 to the 6th joules per kilogram, but here we are looking at it in that form, so whatever. This will be related to our steam. And we've also got the latent heat of fusion for ice, and that's quite a bit less. In fact, stunningly less. It's much easier to melt ice than it is to condense steam or to boil water. 334 kilojoules per kilogram. So this already makes me feel like the temperature of our mix might be kind of high when we're all finished. That's because it's gonna take way more energy to condense some steam than it is to melt some ice. So I'm just thinking, the neat thing about these problems where you've got different phases is you kind of have to play a game. You kind of have to see, well, does this work? Does this work? My intuition tells me we might be able to melt all the ice and still have some steam left over. And here's what I'm able to do. Because of this ratio, I'm able to say all ice melts. Watch this. All ice melts once, wait for it, 334 divided by 2258. This is a ratio, and I'm going to say once 334, 2,258ths of the steam condenses. That's pretty crazy. That's a very small fraction of the steam. It's less than 20%. More than 10% of the steam has condensed, but all of the ice has melted. So now we've got water, and now I'm not gonna say that we've gotten a certain number of kilograms of this business, but I am gonna say, so now we have 1/2 water. Oh man, this is gonna be a little annoying. We've got 1/2 water, and well, we've got 334 over 2258. This water is at 0 Celsius, and this is, oh gosh, times 1/2, right? Because that was half of our original mass. Oh man, this is not the best way to do it. Let's just forge on. Sorry, it's not super clear. Here's what I'm doing. I'm saying that I've never used this camera before, but my other camera's battery died and I'm on a roll right now. So I'm gonna say that this is a fantastically small additional contribution to the loss of steam. And ultimately, what we're gonna have is quite a bit of steam still left and a whole bunch of water at 100 degrees Celsius. That is our final mixture. So let me get some numbers onto this because I've been shuffling around a little bit. But my final argument is that this water will have entirely remained at 100 Celsius. This water will have heated up to 100 Celsius, and this steam will have lost just a tiny bit more. So let me write out that fraction right there. That's going to be 1 minus 334 over 2258, and further minus 0.4 over 2258. You think steam notices when it's heating up a tiny bit of water? You think steam notices while it's burning the legs of my nephew? No, not much. Steam has an enormous amount of energy latent within it. That's that latent heat hidden and sneaky and ready to destroy your skin. Okay, so let's do some calculations. Let's assume that we had 1 kilogram. I want 1 kilogram water and 1 kilogram. That's kind of stupid. Of course, it's all H2O. I want 1 kilogram ice to start with and 1 kilogram steam to start with. And I'd like to figure out how much of the steam is left. So here's my plan. I'm going to take one. Now, I don't need that half because oh, fine. Okay, I'm going to do a ½ kilogram and a ½ kilogram because then I can actually use this number that I've got right here. I'm going to take 1 and I'm going to subtract 334 over 2258, and I'm going to further subtract 0.4 over 2258. That's within my margin of error. Holy cow. So I'm going to take that number right there, and I'm going to divide it by 2. Not 5, but 2. All right, that's how much steam we have remaining. We have... Golly, I can't even write. How annoying. Okay. I think that 0.426 kilograms of steam remain. So we must have, let's see, 1 minus that stuff right, 1 minus that stuff right there, we must have 0.574 kilograms of water at 100 degrees Celsius. That's the answer to the question. Goodbye! Celsius collide and mix. I want you to notice there are 2 key ingredients they've given to us. First of all, okay, fine, I'll say that equal mass is important. But notice this says melting ice. Now that means that the ice is at 0 Celsius. And they say the steam is at 100 Celsius, and so we got equal masses, and they're both about to change phase once the steam has condensed. So I wanted to do this problem, but I got really distracted because I looked up some numbers. So let me show you, I'm going to walk you through. If you want to skip ahead to this time right here, you could just do that. But in the meantime, if you're interested in steam and ice, I kind of was, I looked up the density of steam, and I found that to be, well, at 1 atmosphere. The density of steam at 1 atmosphere apparently is 0.590 kilograms per cubic meter. And then I fiddled around a little bit and found the density of ice. So all we need to worry about is the fact that the changing of the phase will take some energy or release some energy, and the changing of the phase will take some energy or release some energy. And then we also have to consider the energy that goes into changing the temperature of the water that results once the ice has melted, or one of my favorite things about being on YouTube is that teenagers all over the world write me and ask me to do their homework for them. There is one particular problem that I like. This problem here, this is really good. It says equal masses of melting ice and steam at 100